So I will follow the example of my colleague. So we stop in the middle. I think it's a very good idea that we stop in the middle. Maybe let's do it for 10 minutes if possible. I will tell you at some point, but it's a very good idea to stop and think a little bit or interact in the middle. Now, in some sense, after following the previous lecture, you will get the idea that physics is periodic in time. And the period is about 60 years. Because in the 1960s, people were very frustrated with quantum field theory for less sophisticated reasons. Because in the late 1940s, quantum electrodynamics was developed, and they made a big progress because they started to get numbers out of nonsense. Because the typical expressions of quantum field theory were infinite, people devised regularization, renormalization, and computed finite numbers with precise agreement with experiments out of something that seemed to be completely nonsensical. So there was a huge progress, but at that point people became more ambitious and tried to look at the strong interactions. The strong interactions were much more complicated. For one matter, there is a lot of massive resonances among hadrons, and the interaction itself is much stronger. So the perturbative techniques ran into trouble very quickly, and people were frustrated and started to try to formulate S matrix theory to the extent that they could at the time, to try to bypass the need to resort to perturbation theory to get any kind of answers. Now, the program was not very well defined. Now people are attacking the same problem after 50 years of study of quantum field theory and various side issues. So we are much more equipped to ask detailed and subtle questions or address complicated problems. So this revival of this of this search is much more solid than it was in the 1960s. Yet, what happened at that time is that Gabriele Veneziano, who was you would call it a master student here in Florence, and then had gone for a PhD to Weizmann in Israel, basically developed, taking it out of the blue, or actually out of the work of one of the masters of mathematics of all times, a formula which is the Euler beta function. The Euler beta function is defined like this. And if the real alpha and of beta are positive, extremely important for us, integral representations. Now, this formula has something which is manifest, the symmetry into alpha under the interchange of alpha and beta. And people were looking for expressions like this, which are a bit different from what you find in ordinary quantum field theory, because in a quantum field theory, say with a cubic vertex, like you heard in the previous lecture, but in a more in a richer dynamical context in which the particles have a propagator, so where you don't have simply zero-dimensional theory, and you have essentially various types of diagrams, and you have to add them, but each of them individually has poles in only in one channel. So you see the first diagram has pole in this channel. So when the sum of the momenta of the two particles impinging in the region hits the mass shell, then the amplitude blows up, but it doesn't have poles in the other channel. And the same thing is true for the other diagrams. So now what Veneziano devised is an amplitude which would have simultaneously poles in two different channels. Now, the amount of information contained here is huge, and it took years to pull it out a little bit. And the end result was very disappointing because people had developed this kind of idea originally to try to study hadronic resonances, mesons. So you would like to describe states that experimentally were showing a link between mass squared and spin, which will emerge also from this formula, but massive states. On the other hand, it turned out, by consistency reasons that will emerge from the following lectures, that this expression should be formulated like this. So there is a dimensionful parameter, and the argument involves these Mandelstam variables. They appeared already, but let me define them with my notation. And unfortunately, I use minus plus plus plus. And minus plus plus plus, it's or minus and a bunch of pluses, as you will see, because I find it more convenient for quantum calculations. When you weak rotate, only the time flips. The other one, everything flips. So, but it's a matter of taste. You can do from one to the other. So anyway, suppose you take this amplitude, and let me take the two momenta entering here for definiteness. And here this will be 3 and this will be 4 that are going out. So the momenta will satisfy the conservation law. And the Mandelstam variables are defined like this: minus P1 plus P2 squared, and T is minus P1 minus P3 squared. Then there is a third one, U, which is minus P1 minus P4 squared. And this amplitude, these three numbers satisfy the condition that this is the sum of the squared masses. In physics, they are real variables, but as you heard already from the previous lecture, it is important in many contexts to look at these quantities on the complex plane. And this is particularly evident for this function. This is a function which is defined on two copies of the complex plane, and the gamma function, in particular, the building block, is a very interesting function, which can be defined by this integral. Again, if the real part of alpha is positive, and it satisfies an important functional equation. This implies in particular that if alpha is an integer, gamma of n plus 1 is the factorial of n. However, now this integral here is defined on the, so if this is the alpha plane, the integral is defined in this half plane. And what is interesting is that you can analytically continue the function using the functional equation. But the discovery, what you find right away, is that there are poles. There are poles at the negative integer and 0. And this you can see, for instance, if you define gamma of alpha equal gamma of alpha plus 1 divided by alpha. And then you see that if you compute, you let alpha go to 0, gamma of 1 is the integral of the exponential, which is 1. But then this object behaves like 1 over alpha. And in general, gamma of alpha behaves like minus 1 to the n over n factorial, 1 over alpha plus n, as alpha approaches minus n. So there is a sequence of poles with residues that oscillate like this along the negative real axis. And so this tells you immediately that this function here, by comparison with the quantum field theory story that we had before, has poles when this argument is a negative integer. And that's true for S and T at the same time. So let's see what happens if the argument is a negative integer. This means that S is equal to n minus 1 over alpha prime. And n, we said, is 0, 1, and so on and so forth. Now, the problem is that it took years to understand that the correct argument was shifted like that. But once you realize that, and I will show you in later lectures why this should be the case. Now, you realize that there is a pole for S equal minus 1 over alpha prime. With the way I wrote this variable, with the way I defined ST and U, taking into account my minus plus 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 story, S, if it corresponds to a pole in the amplitude, it should identify the square mass of the particle that is interchanged. A square mass that is negative, it's something that in quantum field theory we're very familiar with. Take an example that you studied in courses, which is very important. It's called the abelian-Higgs model. It's actually the model that Higgs proposed originally for his mechanism. So you have a photon, then you have a complex scalar, and then you have a potential, which let me write it like this. Now the potential is what people call a Mexican hat. And then if you take this theory and you expand with respect to this point P, the standard model is a complication of this. You will have a higher dimensional potential, but it's similar in structure. If you expand the theory around this point, then you will find a scalar mode of negative mass squared, the tachyon. But then you know that you're not doing the right thing. You should expand with respect to any of the minima here. And if you expand with respect to the minima, then you find an oscillation here. And an oscillation, first of all, this is a complex scalar, of course, because you have two independent directions to go. So if you're on top, you have a complex scalar to real scalars with negative mass squared. You're not doing very well. You expand with respect to the minima, then you find two oscillations here, a priori. This has positive curvature, therefore positive mass squared, and then the oscillation around the valley costs nothing. That's what usually people call a Goldstone mode. But the Goldstone mode in the presence of this photon field is eaten and makes the photon massive. So in any case, you don't have any tachyonic mode if you expand with respect to the proper minimum. But in order to do this, we had to understand globally, if you want, the phase space of the model and move from one extreme to another. Now, in string theory, we are still not able to do that. And so people had to live originally with this expression, and to some extent we have to live with it still now. To be really more precise, with this type of expression, which as you will see will concern open strings, we know how to go beyond, and we know what happens if you go to the minimum. When gravity is switched on, we don't know really what to do. Coming back to that expression, let's see what happens to that expression if I compute it next to the pole at one of these generic points. So the first gamma function there will become minus 1 to the n over n factorial, 1 over minus 1 minus alpha prime s minus n, the formula I showed you before. And in the factor, we simply use, in the residue if you want, we simply use the expression. So instead of having minus 1 minus alpha prime s, we have in the denominator minus 1 minus alpha prime t minus n. Then the functional equation tells us that this is a polynomial of degree n in t. Now, as I will show, and actually I will show it now so that because it's useful to do it, this t variable is has essentially to do with the scattering angle. The fact that you have a polynomial of degree n in t is a clear sign that the amplitude describes the exchange of particles which have spin up to n. If you want, the angular dependence reveals the number of derivatives that are in the Feynman vertices. And so the fact that you have spin up to n is a tricky story because n is arbitrary. So if I increase the number of n, the spin of exchange particles increases without any bound. So this amplitude really went beyond quantum field theory to an incredible extent. We are describing a theory where you interchange particles of arbitrary spin. Now this is essentially what people wanted to describe phenomenologically, the fact that you had these linear Regge trajectories, which means that the resonances, the hadronic resonances were ordered almost linearly in trajectories where the mass squared and the angular momentum, say the spin of the particles, were related. So the mass squared and the spin is related like that. Now, this is reflected because this particle has a mass squared determined by n. S is the mass squared. And the spin of the particles have to go up to n. They are not simply n, because you don't describe a single Regge trajectory, but you also have this subleading Regge trajectory. But nonetheless, you have this linear relationship. But the problem is that you're going beyond field theory in an incredible way. You have particles of arbitrary spin. Very complicated. And yet, I mean, the effects of these particles build up into an amplitude which is very nice. It has this property. Let me just now be precise with ST and U. So let me go to the center of mass frame. So the momenta will be E and P for the impinging particles, and respectively E and minus P. And the momenta for the outgoing particles, this is an elastic scattering, will be E and P prime, and P4 will be E and minus P prime. So when you compute S with my signature, S is 4E squared. No, because it's the sum of these guys squared. There's a minus sign, but there's an extra minus sign because of the signature. Okay, the momenta will go 0. If I compute T, on the other hand, T, here there is minus P minus P prime squared. P minus P prime squared is P squared plus P prime squared minus, sorry, with the minus sign here for these guys, plus 2P dot P prime. Now, P squared and P prime squared are the same because particles have the same mass. No? You scatter two particles that enter in this region, the particles go out have the same mass, and so this T is equal to, I can write it minus 2P squared. And now this guy is also similar quantity, but there is the cosine of the scattering angle. And now, if you divide by 2, this expression becomes minus 4p squared sine squared theta 1, 2, 1, 3, sorry, I should call it, over 2. So anyway, it's what I promised. I mean, it has to do with the scattering angle. Now, this p squared is essentially S, because the energy is E squared is P squared plus M squared. And so if you want, if we are going at high momenta, which is the most interesting part, this is essentially minus S sine times squared theta 1, 3 over 2 for high energies, where the mass is negligible with respect to the absolute value of square of the momenta. So there was this amplitude. It was a bit of a puzzle, right? Because you had this amplitude here. People didn't know how to write the exact argument. Now it's a bit anti-historical what I'm doing here, because I know that the argument should be precisely like that. And that was already a disaster for hadronic physics, because you are describing a spectrum which contains an instability, a tachyonic mode, which shouldn't be there. The other more embarrassing story will come out from the following lectures, that this formulas make sense if you live in a space which has not 4 but 26 dimensions. So you can imagine the embarrassment when our colleagues decades ago were going to give around seminars about hadronic physics, and people were asking them about this little detail. That was a bit puzzling, right? 26 dimensions for hadronic physics it's not quite right. I mean, something that doesn't quite work. But then there is another interesting property of this amplitude, and if you want, this property is in some sense the deepest and most important property of the amplitude itself, but it sort of killed the applications of hadronic physics altogether. So you see, let me give you a comparison. Just take a look at this formula. You see that those amplitudes there go to 0 like a polynomial in the momenta. Now, what I will show, or give you some details to show, is that this amplitude, if you look at it at fixed scattering angle, notice fixed scattering angle means something very important here. I told you that t is essentially s times the angle. So if the angle is fixed, we have to look at the asymptotic limit of this formula for t and s going simultaneously to infinity, albeit with a relative ratio. Now, what happens if you compute the amplitude in this limit? You find that the amplitude goes to 0 exponentially in s, exponentially. So the amplitude behaves not like a power. So in quantum field theory, one little detail which was implicit in what I was telling you, this is a 3-level amplitude, like the amplitude that were discussed in the previous lecture. How do you tell that something is a 3-level amplitude? Because an amplitude which has only poles is a 3-level amplitude. When you have amplitudes which have more complicated singularities, cuts, then they are loop corrections because they correspond to having intermediate states with two or more particles. So this is a 3-level amplitude. In quantum field theory, a 3-level amplitude goes to 0 like 1 over p squared, say, if you're lucky. Times some powers on top. It could be worse. But you know that now we understand what it means if it's worse. That the field theory that you have makes sense until this type of behavior is not too affected. For instance, the Fermi theory of weak interactions is working up to a certain scale because the amplitude don't go to 0 like this. They have polynomial corrections on top, and the polynomial correction should not be too strong, otherwise the theory ceases to make sense. This is the concept of effective field theory that now is central to what we understand. But in any case, let's say, superficially speaking, this goes polynomially. In string theory, so in the Veneziano amplitude, say the amplitude goes to 0 like e to the minus alpha prime s. Notice that it's crucial to have a dimension full parameter, otherwise you couldn't write that. If you want to write an exponential function, you need a dimension full parameter that couples in front of s to give you a pure number, and here you have it. This is called the Regge slope. It's called the Regge slope because it has to do precisely, if you want, with the slope of this s as a function of n, see, linear function of s as a function of n. N is the highest spin that is interchanged by this argument of the poles that I gave you before. And so that's why it's called the Regge slope. Now, the important property of the amplitude is that it goes to 0 exponentially in s with that exponent. Now, when people were applying this setup to hadronic physics, alpha prime should be a hadronic scale. So you must have a scale of some, say, 100, 200 GeVs. And then when people were doing experiments on deep inelastic scattering at the end of the 1960s, rather than seeing something fluffy like this, they saw something which was very hard inside hadrons. They discovered quarks, if you want. And so the behavior was more like this than this. And so this thing killed the theory completely. But in fact, it's the most beautiful property of this theory, because you see, in such sense, it's telling you that the theory has no ultraviolet altogether. But for that application, it was a disaster. Of course, how can you reconcile this and this? But change alpha prime, change the scale. If alpha prime S is of order 0 at the energies which are relevant to hadronic physics, then this effect of damping, you don't see it. If it's of order 1, then you start to see it. And now you will see that the development is really changing the meaning of alpha prime and the meaning of the setup altogether. Let me give you an idea of how this thing can be proved. Maybe I will not go through all the steps, but I will show you. Now, the first important fact is that gamma, there is a very useful approximation of gamma, which is called Stirling's formula. So if you want to compute gamma of 6 or 7, it's enough to compute it on the right-hand side. You see, it's very precise. It's the basis of statistical physics, if you want this formula, but you don't need to go to the Avogadro number to make it useful. 6 or 7 is enough to get a good... So what happens is that you take this expression here, you take the absolute value, and then you compute gamma of minus alpha prime s minus 1, gamma of minus alpha prime t minus 1, divided by gamma minus alpha prime s plus t minus 2, and you take the absolute value. Then you apply Stirling's formula, and you use this expression. And you will get an expression here which contains a power of t over s and the power of 1 plus t over s. Let me tell you what powers they are so that I don't go into... So the power are minus alpha prime t minus 3 halves. And the power below is minus alpha prime t plus s minus 5 halves. Now the point is that t over s, from what I told you, is essentially a sine squared. And 1 plus t over s, by elementary trigonometry, is cosine squared. And so what happens in this expression is that you will find that the amplitude behaves like e to the alpha prime s times some factor which is square root of s effectively, but the important part is this one. And then you get sine squared theta 1 3 log of sine squared of theta 1 3 plus cosine squared of theta 1 3 log of cosine squared of theta 1 3. Simply by using Stirling formulas and going like that. Now you notice that this expression is of the form x log x plus 1 minus x log 1 minus x. And this expression is a function that has this type of behavior in 0, 1. So it vanishes at the two ends and there's a minimum here, which is of order minus log 2. In fact, it is minus log 2. So this gives you this estimate that typically for intermediate scattering angles, you get minus alpha prime s log 2. Before I didn't show you the log 2 there, but I mean the amplitude goes to 0 exponential in s. And as I said, this for hadronic physics was a disaster, but this is a fantastic result. It's a fantastic result which has a deep bearing on the behavior of gravity. Now, to come to that point, first of all, we have to consider carefully the integral representation for the Veneziano formula. And the integral representation is this. It's integral from 0 to 1 dt x to the minus alpha prime s minus 2, 1 minus x to the minus alpha prime t minus 2. Not too long after Veneziano invented that formula, Shapiro and Virasoro invented another formula, which is less straightforward if you want, but is very similar conceptually. And the formula runs like this. The variable is not on the line, but it's on the complex plane. You integrate over the complex plane, and the integrand here is z to a certain power, which is minus 4 minus alpha prime s over 2, and 1 minus z to the minus 4 minus alpha prime s over 2. Now, if you think what the absolute value of something means, there is a square root, right? This thing it means square root of x squared plus y squared. Now, if you take the square root into account, the actual exponent there is minus 2 minus alpha prime s over 4. And here is minus 2 minus alpha prime t over 4. Sorry, this is not s. So if you think that the absolute value contains an extra square root, then you see that the exponent here is a very close cousin of the other one. The only thing is that this coefficient of s is divided by 4. So Veneziano invented this formula where the integral is over a finite interval along the real axis. And I stress finite. And this is an integral over the whole complex plane. Okay? The integrand is conceptually similar. It's sort of a complexification of the other one. The exponent is also similar if you sort of take into account that the absolute value has a square root in it. So what has changed between one representation and the other is that the Regge slope has been divided by 4, if you want, in the second case, or the masses have been multiplied by 4. The reason is the following, that you can compute this integral. I can even tell you how to do it, because the other one is more straightforward, but this is more complicated. Let me show you what happens if you compute this integral and you find the final expression. First, I will write it to you, and then I will sketch you how to do it. Now, the expression is the following. To be really, so just as a comparison, this expression here is gamma of minus 1 minus alpha prime s, gamma of minus 1 minus alpha prime t, divided by gamma of minus 2 minus alpha prime s plus t. Now, this expression is very interesting because this expression is equal to 2 pi. Now, 2 pi comes because I defined this guy to be dx dy over 2. So if you want, you don't put this guy, you get 4 pi, but I could normalize it. Let me do it like this. So let me do it in more conventional terms. Maybe it's more useful for you to remember this formula like this. So I define the integral with the standard measure, dx dy, and then I divide by 4 pi here. Then the result that you get is gamma of minus 1 minus alpha prime s over 4, gamma of minus 1 minus alpha prime t over 4, and here's the surprise, gamma of minus 1 minus alpha prime u over 4. Remember that there are three Mandelstam variables, s, t, and u. The expression of Veneziano is symmetric in S and T, doesn't know anything about U. This is totally symmetric under S, T, and U. And then here you get gamma of 2 plus alpha prime S over 4, and then so we can repeat the same computation that we did before. Where are the poles here? Well, there are poles in S, T, and U. Right? But what do the poles represent in quantum field theory? Why does this diagram here have a pole? Let me use the same labels, no? This is 1, this is 2, this is 3, this is 4. Why does this guy have a pole in 1, 2? And this guy has a pole, say, in 1, 3. And this guy has a pole in 1, 4. Sorry, it's in 1, yeah. Let's see, what is it? No, this is, let's see, this is 2, this is 4, and this is 3, and this is 1. So the way I wrote it doesn't work. This is a pole in 3, no. It's not good, sorry. I must write it like this, 1 and 3, of course. So you see, this guy is a pole in 1 and 4. So why does a diagram in quantum field theory have a pole in 1 and 2? Because the amplitude allows you in coordinate space, not in momentum space, to squeeze the 2 points next to each other. And here you can squeeze the 2 points, but you cannot squeeze 1 and 3. Here, this amplitude has poles in S and T. So this means that this amplitude here, in some sense, allows me to do at the same time, or independently rather, 2 types of squeezing. 1 and 3, and here 2 and 4. So I can squeeze them. I can squeeze 1 next to 2, I can squeeze 1 next to 3, not 1 next to 4. And now, this tells you about something about the geometry that is underlying this amplitude. It tells you very clearly, with hindsight, of course, because it took years for people to understand this story, that this amplitude has to do with a disk. So in other words, the particles, the analog of the particles for this case, are like little strips emitted from the boundaries of a disk. Now a disk can be deformed, and you can get these 2 lines close to one another, or you can get these 2 lines close to one another, but you cannot get this close to this because you have to pass through another line. And now, from this point of view, you can also understand why this amplitude has poles in the 3 channels. Geometrically, it means that it has to do not with the disk, but rather with the sphere. And the 4 external legs that can move freely on the sphere, or rather that the amplitude results from a sum over paths where the external legs are everywhere on the sphere, then clearly there are limiting regions where this comes close to this, or close to this, or even close to this, because they don't need to cross the other, they go in a different direction. So Shapiro and Virasoro invented an amplitude which has what is called, what used to be called nonplanar duality. Duality is one of the most abused terms in physics. No? So today it means many things. At the time, planar duality meant that you have this property of being able to squeeze 2 legs into different ways. So in retrospect, that the amplitude had to do somehow with a disk, with some punctures. Let me call them punctures. You take a disk, you put some punctures on the disk. Let me do it like this. Think of it like this. Punctures can move around the disk, and then in moving, these 2 punctures can hit each other, or this can be hit, but this cannot hit the other one. But punctures can move in a sphere as they please, and then they can hit each other in any possible way. That was the nonplanar duality of Shapiro and Virasoro. So that's what happened with this thing. Now, in order to show this, let me give you a hint. I mean, first of all, I mean, you can prove all these identities in various ways. Maybe I can do it here. Maybe there. So let me sketch you the proof of that. And no, sorry, before I do that, the poles I told you, I can look at the residue now, because I can stick here in the, remember that S plus T plus U is the sum of the mass squared, no? In this case, it's 16 over alpha prime, actually minus 16 over alpha prime, if I consider the 4 tachyons that are emitted. No? The amplitude that Veneziano invented is the scattering amplitude for 4 tachyons, the simplest particles, scalars. There's no polarization kinematics there, just momenta. So they are scalar particles, that's clear. The fact that they are tachyons, maybe it's something that became evident a little bit later from the form of this integrand, but let me tell you that they are tachyons. For the Veneziano, for the Shapiro-Virasoro, this is the condition. For the Veneziano, S plus T plus U is minus 4 over alpha prime. Remember, there is a factor of 4 in the poles, no? Because there is alpha prime over 4 in the second amplitude. Now, before in Veneziano, I showed you that if I go near the pole, then this ratio here, computed at the pole, rearranges itself into a polynomial of degree n. Here, if you go near the pole, what happens is that you pull out this guy, and then the rest of the story, now this guy becomes a positive quantity, and so if you want, it's a finite quantity, but these ratios here become, it's actually a number, no? Because S is fixed at that point. Alpha prime S equal 4 is n minus 1, so this guy becomes n plus 1, so it's 1 over n factorial if you want. But these ratios here become polynomials in T and U. And now if you look at it more carefully, it becomes the square of the type of expression that you had in the Veneziano. So it means, if roughly speaking, that the spins go up to 2n in the Shapiro-Virasoro. In Veneziano, they go up to n. In Shapiro-Virasoro, they go up to twice n because of this factor. But nonetheless, the pattern is similar. You have an infinite number, you are describing amplitudes which come from some sort of structure of entity that contains infinite many states of arbitrary high spin, and not only infinitely, twice infinite, because this spectrum here has nothing to do with this, apparently. It does, but in a deep way. But it has nothing to do with it in the sense that they're different particles. 2 infinities of particles, and the spin is twice as high as in the other case. At least the bound, and then there are subleading trajectories. Now, before I conclude this first part of the lecture, I tell you this story. First of all, remember that gamma of alpha is integral from 0 to infinity, e to the minus t, say, let me get u to the alpha minus 1 du. And now suppose you compute gamma of alpha, gamma of beta. This becomes a double integral from 0 to infinity, e to the minus u plus v, u to the alpha minus 1, v to the beta minus 1 du dv. Now change variable, define u equal xi times zeta and v equal xi times 1 minus eta. Then you can see that the Jacobian becomes xi di xi di eta. This is a trivial derivative, compute the determinant there. The range, clearly, since u and v are positive, then clearly eta is bounded. So eta is bounded between 0 and 1, and u and xi is from 0 to infinity. Now suppose you do this, you get integral from 0 to infinity, xi di xi, integral from 0 to 1 di eta. This exponent becomes simply e to the minus xi, and then this guy becomes xi eta to the alpha minus 1, 1 minus eta times xi to the beta minus 1. And now let's count now the two integrals factorize. What is the power of xi? You see, it's alpha minus 1 plus beta minus 1 plus 1. So you get integral di xi e to the minus xi to the alpha plus beta minus 1. I repeat, alpha minus 1 plus beta minus 1, which would be alpha plus beta minus 2, but there's another xi from the Jacobian, you get this. And then the integral of eta becomes d eta, and then becomes eta to the alpha minus 1, 1 minus eta to the beta minus 1. So this quantity is gamma of alpha plus beta, and this equation inverted tells you precisely that this expression here this integral of the Veneziano amplitude is the ratio of gamma alpha, gamma beta divided by gamma alpha plus beta. Now, in the other case, in the Shapiro-Virasoro is more complicated. You have to start from this expression that z to the minus a is integral from 0 to infinity du e to the minus u z absolute value squared. And here you have u to the a over 2 minus 1, du I wrote it already. And this expression is gamma of a over 2 times this. This is the usual definition of the gamma function up to this rescaling here, which you can pull out by the changing variables, and you get this factor. Now, this you have to use twice. You have to use it here and here. So you use the z, so this expression here becomes an integral with z absolute value squared in the exponent. The other guy becomes an expression with 1 minus z absolute value squared in the exponent. And so the integrals that you have in x and y give you two Gaussian integrals, which you can perform. If you perform the Gaussian integrals, then you're led to something like that redefinition that I showed you in this more elementary case. And that eventually leads to the Shapiro-Virasoro formula. So what I showed you so far is where people were between 1968 and 1970. Because in 1970, a big development took place. People started to understand a little bit why you had this structure that resembled something where these punctures could move around the boundary. Now, it's a bit strange if you think about it, that the boundary, by conformal mapping, can be turned into the real axis. So if you wanted to, quote unquote, sum over paths, you should sum over the positions of 4 points on the real axis, which is from minus infinity to plus infinity, and you just integrate over a small integral from 0 to 1. The reason is that there is a big symmetry, and you have to do something similar to the gauge fixing procedure that you do in quantum field theory when you integrate, path integrate over gauge fields. I mean, you get an infinite, here it's not a local symmetry, it's a global symmetry, but yet it's a non-compact global symmetry. There is a group of transformations of infinite volume, and when you have something like this, you have to be careful, otherwise you get infinity and that's it. So in order to, this group of transformation is nothing but this group of fractional linear redefinitions with real coefficients. So in general, in the complex plane, you have this group. This is SL2C, or to be more precise, is SL2C mod Z2. Mod Z2 because you can flip the sign of all these coefficients and nothing happens, not because they are, there's a fraction. This is a one-to-one map between the Riemann sphere and itself. Now, if you want to leave the real axis fixed, then you should use real coefficients, and then you have SL2R. By this map with real coefficients, you can move the points everywhere, or rather fix 3 points at 0, 1 at infinity and infinity. The fourth point will move between 1 point and the other. And that's your Veneziano integral. So you have 4 points. A priori, you should integrate over the real axis, because the real axis is the conformal map of the boundary of a disk. You don't do it because it's a trivial infinity. You fix the 3 of them. I should stop. We continue later because okay. 10:20? Okay, should we start?
Yes.
Okay. Before going further, I want to stress another important point that was only appreciated in the 1970s and better understood in the 1980s. The Veneziano amplitude actually has another property that in retrospect is clear from this picture of the disk I told you. So this is 1, this is 3, this is 2, and this is 4. And so this quantity is S and this quantity is T. But you see that if I take this amplitude and I cycle the external legs, so if I let not 1, 2 here, 1 here, 3 here, and 4 here, then the poles remain the same because the adjacency of the external points is unaffected by cyclicity. So in other words, the amplitude is cyclically symmetric. And so what people did in the 1970s, early 70s, so it's this first phase of interest in the story, they tried to give these particles what you could call a flavor quantum number, so add the global symmetry. And in other words, they did the following. They took the amplitudes, let me write it here symbolically, 1, 2, 3, 4, and they multiplied it by the trace of lambda 1, lambda 2, lambda 3, lambda 4. Sorry, lambda 1, lambda 3, lambda 4, lambda 2. Same order. Plus, now 1, and then cycle the other two. It's 4, span 2 become 3. And then this you multiply by trace of lambda 1, lambda 4, lambda 2, lambda 3. And then you add the other amplitude, which is 1, so 1, 3. So this becomes 1, 2, 3, and 4, no? So this is trace of lambda 1, lambda 2, lambda 3, lambda 4. So in other words, you can take 4 matrices to be specified, and you can multiply the amplitude by another expression built out of these 4 matrices, which shares the same cyclicity property of the amplitude itself. In this fashion, you endow the particles with an internal quantum number. And originally, people thought it was a global symmetry that you were adding. Actually, it turned out to be a local symmetry, as we will see later. These factors are called Chan-Paton factors. And they're very important. The observation is the following, that this quantity here factorizes near the pole as we discussed before, no? If I go near the pole at alpha prime s equal n minus 1, this amplitude factorizes in the product of an amplitude like this, propagator, amplitude like that. The propagator, you saw the propagator coming from the 1 over s plus n, no? The pole of the gamma function. This factor here, so I'm looking at this quantity here. I'm looking at this quantity here, say, because this I can cyclically write the way I wrote it before. Is accompanied by this factor, and this factor Bechter factorizes exactly in the same way. Otherwise, you would violate the unitarity of these amplitudes. Now, this factorization is guaranteed if the lambda matrices are a complete set, which is the case for unitary groups. Unitary groups are described by the matrices of the adjoint are Hermitian n by n matrices. And in a Hermitian n by n matrix, you can write any Hermitian matrix as combination of that. So if you want it's a completeness condition of the type of what you saw before with 2 by 2 matrices. That's the case of SU2. I'm talking about UN, not SUN. So in other words, if these matrices are matrices of UN, I can write this thing as a trace of lambda 1, lambda 4, lambda I, trace of lambda I, lambda 2, lambda 3, times the coefficient, because the sum of lambda I, say lambda I alpha beta, lambda I gamma delta, this object here, is essentially a delta beta gamma delta alpha delta. Actually, if I were more precise, I would raise one index here, and then it would be more clear why they contract like that, beta gamma alpha delta, like this. So in other words, I can factor in the same way as you factor near the pole the amplitude, even this group theory factor. And that's why people started to, basically they were doing U2 or SU2, but SU2 works for an accident because SU2 is SP2. So that's the reason why for the 2x2 case it works. In general, you need UN matrices. Then in the 1980s, it was re-examined and it was shown that in fact you can be even more general than this. Because the Veneziano-like amplitudes, actually they are called Koba-Nielsen amplitudes in general. The Koba-Nielsen amplitudes are the analog of the Veneziano where you have endpoints here. And as you can imagine, by analogy with Veneziano, you have nested integrals in which you move n minus 3 of these external points. You fix one at 0, one at 1, one at infinity, you move the other ones in the middle by nested integrals with an integrand which is similar to that one. So this amplitude also factorizes in internal poles, and then you can decorate it with group theory factors. However, the amplitudes have another symmetry, which was overlooked originally, and A of 1 and n, this Koba-Nielsen amplitude, A of 1 and n, is proportional to minus 1 over n plus the sum of the mass squares times A of n and 1. So in other words, if you take the amplitude, that doesn't only have cyclicity, but it has this symmetry property. You can flip all the order of the terms. In fact, it's called flip symmetry, up to a sign which depends on the mass squares of the external particles. Now, for Veneziano, it's fixed, but in principle, you can compute the analog of this amplitude, this generalized Koba-Nielsen amplitudes for external particles of arbitrary mass. Where they come from, you will see it now. But what I wanted to show you is just that you can decorate the amplitude by these Chan-Paton factors. And in the 1980s, taking into account the flip symmetry, it was understood that you have 3 infinite families of choices: the orthogonal groups, the symplectic groups, and the unitary groups, but not the exceptional groups. You know Cartan's classification of simple Lie algebras. No, there are 3 infinite families of matrix algebras, plus a finite number of exceptional algebras, which are G2, F4, E6, E7, and E8. Those ones do not allow to be used in Chan-Paton multiplicity, in Chan-Paton, say, factors, because they don't factorize in this way. The factorization of unitary groups is straightforward. For the orthogonal and the symplectic, you have to work with adjacent ordering using the flip properties. They go 4 amplitudes conspire to factorize in that case. Now, what do people understand? Well, they understood that you have a spectrum of states which are linear in some quantum number. And that's very reminiscent of something that you studied in elementary courses on mechanics, which is the vibrating string. Now, the vibrating string should be very sophisticated in this case because it has to be compatible with relativity, special relativity at least. And so it should be a more sophisticated way of formulating a vibrating string. But more or less, the fact that the spectrum repeats itself like this makes you think about that. So how do you describe a relativistic string? First of all, start with a particle, and the particle has 2 different representations. This is the usual one. I'm working with C equal 1, like in the other lectures of my colleague. And this is the standard representation of a relativistic particle. Okay. the Lagrangian gives you, of course, you can add, say, an electromagnetic potential or other terms, but I mean, this will tell you only that the velocity is a constant, it's a free particle, but it's a free relativistic particle, so you get the relativistic definition of momentum, if you want. Now, what people realized is that for a vibrating string, you would have an analog of this expression, which would be very natural, which is the area swept divided by the string in its motion. So the particle describes a trajectory, and so in some sense, this is a length of this trajectory. A string sweeps an area, because if the string, say it's open, it moves in this direction, it sweeps an area. So what Nambu and Goto proposed, and actually not only them, there was also Nielsen and Saskin. There were 4 people that were somehow getting that at that point in the 70s, to propose an action which would give you what we got there out of that spectrum, starting from the area swept by a vibrating string. In retrospect, it was complicated. It's very simple to bring it to the same point, but people, as I will sketch, but people did better in the 1980s. The reason why they did better in the 1980s is because already for the particle, you have a better way of describing it. You can define the action for the particle in this form. And then you can add to this expression. So you introduce some sort of a, you could call it Einbein, some sort of a one-dimensional analog of the square root of the metric. This is the analog of the square root of minus g, if you want, here in 1 dimension. So that this expression is manifest invariant under reparametrizations. And then this quantity E, which is some sort of a gravity along the world line, is a Lagrange multiplier. So you can eliminate it by its field equation. Let's see, maybe I made the wrong error. I made the wrong sign with this thing. I think I did. There should be like minus sign here, maybe. So if you vary with respect to E, then you get an equation which is like this. Times delta E, no? I'm dropping delta E. Therefore, if you take this expression here and you multiply by E, you find that ME can be replaced by 1 over E times d tau x mu squared. No? So in other words, the 2 terms are the same. So you can replace this thing by M integral of ME d tau. So you gain the factor of 2. And then having ME, if you take this equation, you take the square root. ME, you can write it as square root of d tau x squared. D tau x squared, and then this expression becomes the previous expression that you had. Because it becomes the integral d tau x squared. So if you use tau equal the time t, then you get square root of 1 minus v squared. So in other words, there is a very simple way of formulating in a quadratic language an action which gives you the relativistic particle action. The same thing you can do for a relativistic string. And then there is a difference that the string doesn't have a mass term. And this endows the theory with an extra symmetry. So you introduce 2 variables locally on the world sheet. I call it d to xi, the integral. Then you introduce now a genuine metric on the world sheet. And this is the action for a string. And you see this action contains an extra information whose meaning was understood later in the 1980s. This is a metric of the ambient space-time. where the string propagates. So in principle, you could also consider a generalization of this theory, and it was considered, where this metric is an arbitrary function of x. So the string could be also let to propagate in an arbitrary curved spacetime. But let's first analyze the simple case, then I will tell you what happens if you, because it's really an enticing story, what happens if you let this metric propagate. So people actually worked with another action, which is the Nambu-Goto action. First of all, we derived the Nambu-Goto action. Okay? How do we derive the Nambu-Goto action? We notice that this is a theory of two-dimensional gravity coupled to these variables x that correspond to this, describe this, the string sweeping the world surface. Okay? But there is no kinetic term for gravity, right? Because in 2 dimensions, the kinetic term for gravity, Einstein term, is a topological invariant. So there's no dynamics in that. So the gravitational equation of motion is simply the condition that the energy momentum tensor of these fields be 0. And what is this equation of motion? It's dax dot dbx equal 1/2 gamma ab dx dot dx, where dx dot dx means dc dd gamma cd. If you want, this is the two-dimensional gravity equation. Now this is a matrix equation. You can take the determinant of both sides. And if you take the determinant of dax dot dbx, then this thing is 1/4 times the determinant of gamma times this object here squared. And now you take the square root with the proper minus sign, and you get the square root of minus the determinant of dax dbx is equal to 1/2 square root of minus gamma times essentially the kinetic term. Altogether, this thing is the kinetic term of this Lagrangian that I've started. So in other words, this thing here could be also reformulated as 1/2 pi alpha prime integral. Maybe I got the wrong sign again. Let me see. Yeah, because if I go with my convention of time, there's 2 minus signs, and then it should be like this. 2 minus signs, yes. So the reason, if you want, is that the time, so to speak, derivative of xi, which are the physical coordinates, should be positive. Anyway, this thing is the expression, and then you get d2 xi. Instead of that expression, you get this minus the determinant of dax dot dbx. It's a pretty scary expression because you have a square root. However, it shouldn't be so scary because that's the object geometrically is the metric induced by the embedding, and you are free to choose coordinates in such a way to simplify this expression. So for instance, you can choose orthogonal coordinate sets, orthogonal lines on the surface, so that this determinant becomes diagonal, and then you can normalize the two directions appropriately, and so this effectively is a field theory in disguise. I'm not going to develop this detail, but you can write the field equations, and then you can see that the field equations simplify by this choice of coordinates. So rather, I will work with this expression. I will work with this expression. This is usually called the Polyakov action, which is unfair, because this action was invented by two groups of people, Brink, Di Vecchia, and Howe, and Deser and Zumino. Not in this form. Actually, they invented the supersymmetric extension of this action. So this is a byproduct of their construction, which was essentially a two-dimensional version of supergravity, if you want, in the mid-70s. What Polyakov did, he used this form of the action to quantize it and try to go beyond what I will discuss here. But the so-called non-critical strings never caught up really as much as people hoped at the beginning. So I will stick with what are called critical strings. the ones in which this famous 26 I told you before about, and another famous 10 will emerge later. So we have to quantize this action. I mean, first of all, we notice that we have a two-dimensional metric which has three components. It's a 2 by 2 symmetric matrix. So it has three components. And then we have two-dimensional diffeomorphisms, which are defined by parameters, say, epsilon, which has two components. However, there is a special feature of two dimensions, namely that if I rescale, say, gamma AB by e to the sigma by a Weil rescaling, this expression here gains an e to the minus sigma because it's the inverse matrix. The determinant would gain e to the 2 sigma, but it's a square root of the determinant, so it gains an e to the sigma. So this theory actually does not depend on the whole metric, but it depends on the metric modulo the conformal factor. So it depends on two data contained in the metric, which are as many as the data contained in the diffeomorphisms. So this means that by a choice of coordinates, one can make this metric diagonal and the conformal factor becomes irrelevant. So if this is the case, then what happens, maybe I do it here below. Then what happens is that the equation of motion for the x coordinates that emerges from that action, which seems complicated because it's a typical gravitational equation, so a priori it's dA of square root of minus gamma AB dB x mu equals 0. It actually becomes the free wave equation. The reason is that is exactly what I told you before, that I can use a coordinate system such that gamma AB is e to the sigma delta, say eta AB actually in the Minkowski case. And then the special feature of two dimensions means that this quantity here becomes eta AB, eta CD, sorry, no, eta AB. So in other words, the equation that I get for x mu is d tau squared x mu minus d sigma squared x mu equals 0. This seems promising because it's exactly what you did at school, done for a relativistic formulation in which x also has the time component. So this equation we can solve. And if we solve it, then we have two, say, most symmetric solutions. This describes closed strings. Normalization is useful because when we quantize the theory, these objects are essentially harmonic oscillators. And then for open strings, notice the doubling of frequency in the other case. The reason is that this cosine and sigma satisfies the condition that the derivative of x with respect to sigma is 0 at the two ends. The length of the interval is taken to be 0 to pi in both cases. And here, if the length of the interval is pi, then this grants periodicity of the coordinates. But notice there is a factor of 2 there. So it seems that we are done. No? It's trivial, right? It's not trivial because we have to solve the other equation. There is a quadratic constraint. The gravity equation is to be solved. So it's more complicated than the vibrating strings you learned about at school because of that quadratic constraint. And now there has been an industry of thoughts and technical developments over the years for how to quantize this system, of increasing number of sophistication, increasing level of sophistication. But for what I'm going to describe to you here, which are essentially the consistency conditions of string spectra, we can rely on what is perhaps the crudest way of dealing with this problem, which is the light cone quantization. What do we lose by the light cone quantization? We lose the manifest Lorentz invariance, but the amplitudes will regain it. So if you compute scattering amplitudes, the amplitudes will embody the Lorentz invariance or covariance, depending on whether you have what kind of particles you have on the outside, although the formulation will be not manifestly so. There is an alternative, which is called the old covariant quantization, in which you quantize covariantly and you try to impose these conditions on the states. Both of these formulations are fine for low-lying states, but for very massive states, they, in some sense, they make the interpretation of the representations involved complicated, inevitably. In the light cone, because you have to reconstruct covariant representations, proper complete representations that for massive modes they contain also longitudinal polarizations by putting together various things. In the covariant form, because you have to impose conditions that eliminate spurious polarizations which are not physical. Then there is the BRST formulation, which eventually led to formulate string field theory, in which you basically study the states in terms of the cohomology of the BRST operator. So you find that the condition of the physical states is that they should be annihilated by the BRST operator modulo the BRST operator on some other parameter. But this is the most convenient way of dealing with this problem is the following. Insofar as identifying the properties of the consistency rules for the spectra, because for instance, we don't know anything. We have the Veneziano amplitude, we have the Shapiro-Virasoro amplitude. Should they be considered together or one is enough? And which one is enough? Now we will find a concise way of dealing with this problem at the price of other details which will be hidden. The structure of the massive states, the geometry that is hidden in the presence of these higher spin states in string theory is completely a frontier topic for a long time, and there is something very deep in the back of that stuff that we don't control but we can tell whether a theory makes sense as a string theory or not in a relatively handy way. So the observation is the following. Let me motivate it by electrodynamics. I like to do this because it's then you see that it's similar. So suppose you take electrodynamics and you have the Maxwell equations. In terms of the vector potential, this equation is box A mu minus d mu d dot A equals 0. And clearly this equation is invariant under delta A mu equal d mu alpha, where alpha here is the gauge parameter. Okay. Now, what you learned at school is that the Maxwell fields have two polarizations, no? Or depolarization, or d minus 2 polarization is the dimension. Let's say 4, for instance. 2 polarization, here you see 4. So there must be some way of getting rid of 2 polarizations. How do you do that? You do it in 2 steps. First of all, you impose the Lorentz gauge. And then you realize that there are additional so first of all, if you impose the Lorentz gauge, then you find something interesting, that A mu satisfies box A mu equals 0. So if you want to consider, say, a wave propagating along the z direction, for instance, it could be like this. Okay. Then If you want to impose the Lorentz gauge on this expression, then you will have to impose that d0 a0 plus d3 a3 equals 0. And now if you see what this thing does, it tells you that epsilon 0 is equal to epsilon 3. Because if you differentiate with respect to time, you get minus IP. If you differentiate with respect to Z, you get plus IP. And so these two polarizations should be the same. 4 minus 1 is 3. We are not done yet. The reason is that there is a second gauge transformation that you can perform on shell that doesn't alter the Lorentz gauge. So I can send a mu in a mu plus d mu of epsilon. And if box epsilon is equal to 0, this redefinition does not alter the Lorentz gauge. Maybe epsilon is not a good symbol. Let me call it lambda. And so this means that if I take a mu, so I take lambda, say, equal lambda 0 e to the IP times z minus t, and then you see that delta a0 is d0 of lambda, delta E3 is D3 of lambda. What is D0 of lambda? Is minus IP lambda. And this expression is IP lambda. However, if I think in terms of the upper components, this thing there is a flip. So this tells us that delta E0 is plus IP lambda, and delta E3 is plus IP lambda also. But A0 was the one characterized by polarization epsilon 0, and this by polarization epsilon 3. So by this single gauge parameter, these two identical polarizations, I can subtract them out. Notice there is this, the important thing is the flip of sign. No? Before, the gauge condition tells us that epsilon 0 is equal to epsilon 3. The on-shell gauge transformation gives opposite values to the shift of A0 down and A3 down. When we flip, when we lift, A3 up is equal to A3 down, but A0 down is minus A0 up. And so the upper components shifted exactly in the same way. We shift them away, and then we get two polarizations, as they should be. And this works for arbitrary spin, for arbitrary case. Now, if you apply to string theory this idea, basically there is a way to do it, which is slightly different. Actually, in this case, you can define light cone components and work with light cone components. So what I showed you here is what to do it in the Lorentz gauge, but it's possible to do it also in what is called the light cone gauge. Why do we need to work with light cone coordinates? The problem is that that expression is a quadratic constraint, and a quadratic constraint on these alpha coefficients, which eventually will become quantum oscillators, is complicated. We want to linearize this constraint. And in order to linearize this constraint, we use a trick. The trick is the following. If you want to take two vectors and compute x mu, y mu, this expression is minus x0, y0 plus x dot y. Now it's convenient to define x plus minus equal 1 over square root of 2, say x0 plus or minus x0 plus x d minus 1. Then this expression becomes x plus y minus plus x, sorry, square root 2 I put it, yes, x minus y plus xi yi. So you see that some part of this expression has become off diagonal. The same thing can be done in 2 dimensions with the wave equation. Instead of writing the wave equation d second tau minus d sigma twice, I can define tau plus or minus sigma, and then write this guy d plus d minus, where this d plus d minus, say d plus minus is d tau. There is actually a plus. No, okay, I write it like this, doesn't matter. Divided by square root of 2. In the In the Euclidean case, this is the relation between the Laplace operator and the and the derivatives with respect to z and z bar that tells you that the solution of the Laplace equations are analytic and anti-analytic functions. No? In the Minkowski case, this is this factorization. It's what leads to the exact solution of the wave equation in 2 dimensions in terms of traveling waves of 2 types, which is, by the way, what was used in this decomposition here. Now, the point is now to use all the freedom that we have, and we do have some freedom still, to simplify matters. And the freedom that we have is essentially to eliminate all the oscillators in the plus direction. So this condition means that there are no oscillators in the plus directions. Okay, and this you can do in both cases. Why can you do that? Because you are essentially identifying x plus and tau. And these are both solutions of the wave equations in 2 dimensions, no? Because the tau squared of tau is 0, the sigma squared of tau is 0, and this one satisfies, we said, the wave equation. So if there are 2 solutions of the wave equation by a change of coordinates, which is the counterpart with the signature of what would be a conformal map, you can identify x plus and tau. The analog of this in electrodynamics would be another choice of gauge, which would be a plus equals 0. Then the Lorentz gauge would tell you that d plus a minus, say, plus d minus a plus di ai equals 0. Now, a plus equals 0 is equivalent to a minus equals 0, no? So this means that this is not there. Then you would see, in electrodynamics, you would say that a plus is minus 1 over d plus, 1 over d minus, sorry, di ai. And then you're left only with ai. You see, the Lightcon gauge is even more direct, no? You just put to 0 one component, you solve for the other. Now, this is exactly the procedure that we will follow in string theory, with a big advantage that working with this off-diagonal metric, if you want, will linearize the constraint. So first of all, these constraints here correspond. How many constraints, first of all, are there here? Let me talk about the closed case. Naively, this is a 2 by 2 matrix equation, but this matrix equation has 0 trace. Because the equation that should be the object that should vanish, if you want, if you think of a term like TAB equal this expression, TAB, since you are in 2 dimensions, the trace of this gamma is 2, this 2-dimensional object has 0 trace. So it means that this 2-dimensional energy momentum tensor has 2 independent components. Now, if we work in terms of these Lightcon coordinates, there are 2 components only. There is a t plus plus and a t minus minus, because t plus minus is proportional to the trace. And I showed you that the trace is 0. So those conditions are 2 conditions. And so what we have to solve here, so we have to use this thing. The idea is that x minus will be solved in terms of the xi. And the xi will be in the independent vibrations. So let's see how it works. So first of all, the 2 conditions that we have to solve, remember that this metric times this inverse metric, the sigma disappears. So basically the conditions are d plus x dot d plus x equal 1/2 and now eta plus plus and eta minus minus are 0. Actually, this is an important point. The matrix eta AB, which is -1, 0, 0, 1, in terms of plus and minus components, there is only an eta plus minus. So in other words, the second part of this story doesn't contribute anything. So the equation simplifies even further. You have this condition, and then you have this other condition. Okay? The dot means that it's summed over mu. Okay? So for instance, this expression here means d plus x mu, d plus x nu, eta mu nu equals 0. Or in terms of plus minus components in space-time, you get d plus, d plus x minus, then there would be another term identical. And then similarly, the same condition with minus. So let's concentrate on this one. Now you see that roughly speaking, you see that this is a linear equation for x minus. And d plus x plus is essentially a constant because the derivative with respect to sigma is nothing, the derivative with respect to tau is a constant. So you see that this equation solves x minus in terms of the other, exactly like in electromagnetism. However, we have to be a little bit more precise in this story because there are some subtleties involved due to the presence of an infinite number of modes. So let me leave that blackboard here and come back to this point. No, not this point. This point we need it. So let's see what happens if we are precise on this story. First of all, let's compute d plus of x mu in general. No, nothing. We need to stop now, and then I continue next time. That's it.